Our final CDT-off presentation will be presented by Jez, Mark, and Tom on the theory and simulation of materials.
That's what we're talking about. Okay. Thank you to all of the other CDTs for their excellent presentations and a brilliant warm-up act. So my name's Jaz, and my job in this presentation format is to take you from seeing this very colourful mouthful, the theory and simulation of materials, and give you a genuine enthusiasm and appreciation for the kind of work that we students in the theory and simulation of materials actually do. So just to kick off on an epic note, every single era of human civilization is defined not by ideas or individuals. It's been defined by the very materials that transform those societies. Now let's think of the Stone Age, the Bronze Age, the Iron Age, and now the Silicon Age. It's for thousands and thousands of years we've been manipulating materials to suit our needs, and they have changed our societies at every single point. However, historically, the study of materials has only been treated as a science in the last 100 years. It's actually one of the most underrated of the sciences. However, in that time, in the last 100 years, we've gone from being able to... we've gone from stone buildings to skyscrapers, from typewriters to touchscreen phones. We've even been able to mimic nature and develop materials that can take light and heat and turn them into usable electricity. Some other examples of some amazing materials that we work on are shape memory alloys. We've got radiation-tolerant materials. These are materials that stay structurally stable even in the harsh reactor environment inside nuclear reactors. We've got ferroelectric materials that can be used for data storage. And finally, we've got temperature-resistant materials that have enabled us to go to the moon and back in one piece. But what's more amazing about material science is that it actually calls upon many disciplines and unifies them in a very powerful way. To solve a problem, we pick up a bit of quantum mechanics here, a bit of chemistry and engineering there. And that's how we bring them all together to try and address real-world challenges. But that's not the end of it. Within the theory and simulation of materials, our tagline is that we bridge length and time scales. Now, this is best described with an example. And the example I'm going to use is that of fracture. Now, when I bend a piece of material, the physics of it is described very well on the continuum scale. However, when a crack forms, our model starts to break down, and we need to probe the material a little bit further to understand what's actually going on. Now, the physics at the tip of this crack here requires a description of the atomic bonding and the breaking of those bonds. Whereas on the continuum, whereas the rest of the material still follows continuum models. And so we see that a phenomenon as very simple as fracture actually covers a vast range of length scales. And so in TSM, our approach is to bridge these two scales of model, probing the crack tip using atomic scale simulations and feeding that into continuum level models so that we can see what the impact of that crack is on the rest of the system. And that's just one example of the kind of things we do. And in order to address these kinds of problems, we need to study a range of disciplines, and that's the kind of thing that we learn during the master's course. And what's more, the students in the theory and simulation of materials, we become fluent in these different disciplines so that we can bridge the gaps between engineers and physicists and chemists to address real-world problems.
Apart from world-class science, outreach is an important component of the TSM, and we actively seek out ways innovative ways to communicate science to the general public, such as through science demonstrations at the Imperial Science Festival or by tutoring pupils at disadvantaged schools. A lot of tenacious projects have been initiated and involved by the students at the TSM. For example, the Hermes 2012 Summer School. After obtaining corporate sponsorship and attracting a global cohort of 50 students, the TSM students delivered the school to teach young researchers how to communicate material science to the general public via the medium of film and stop-motion animation. The Solar Park Spark project focused towards solar power outreach, and London's regional chief organiser is one of our TSM students who has travelled to as far as Aberdeen to give demonstrations at the British Science Festival and more recently the Big Bang Fair in London. And a few of our students at the TSM have decided to take their simulation skills and put them on the cloud so that the general public play around with dynamic simulations of water, offering insight into the complex physics of this seemingly simple substance.
Nathan, we were told that we could only have 3 people presenting in the CDT-off, although it seems like the CQD didn't go along with that either.
Ferroelectric materials are useful for a whole range of electronic devices, such as random access memory. I have developed a very simple model for the bonding in these materials, which is really efficient to run on a computer and gets us close to quantum mechanical accuracy. And this means we can really probe what's happening within these materials on the atomic scale.
I'm working on a material called ultra-high molecular weight polyethylene. It is light and incredibly strong, which means it can be used for a vast range of applications, including bulletproof vests and satellite shields. I'm trying to come up with a physical model to describe the experimental results that have already been obtained on this material. This will help to explain some of the limitations and possible improvements on the material.
I'm taking a simulation technique called molecular dynamics, which follows the motion of atoms in a material, and making it much faster using a method known as coarse graining. I do this by grouping atoms into blobs and treating each blob as a self-contained unit. These simulations are commonly used for drug discovery in the pharmaceuticals industry, and I'm trying to make this process faster and cheaper so that we can model even bigger systems.
I am about to start my project about hydrogen diffusion in metals, and this is very important because hydrogen causes embrittlement. I will study how the presence of vacancies affects the diffusion and the thermodynamics using Feynman's path integral, and by doing so, I hope to bring the quantum effects to a larger length scale.
I work in computational nano-optics. My group studies the interaction of light and matter. The information we gain by doing this enables us to build new devices that can detect explosives in airports and classify diseases in hospitals. And maybe one day we will even build that invisibility cloak that we have been promising for all this time.
When we think about the solidification of metals, we have a liquid phase in contact with a solid phase. What's interesting is that there's an energy associated with creating an interface between these two phases. How large this energy is actually affects the way the metal solidifies and therefore the final microstructure. I use quantum and statistical mechanics to calculate this energy, which can then be used to create more realistic models of solidification.
Inside pressurized water reactors, zirconium alloys form a protective barrier between the fuel and the outside world. However, hydrogen from the water seeps in and forms hydrides near cracks and causes embrittlement. Well, to study this phenomenon, I combine atomic scale calculations with analytical models to simulate the way hydrogen diffuses along stress gradients to these cracks.
Contrary to popular belief, size matters, at least on the nanoscale. So I'm doing large-scale quantum mechanical simulations on nanomaterials to understand how they behave under pressure and how their unique properties can be tailored for applications such as photovoltaics and nanosensors.
I'm part of the TSM master course, and for one of my assignments, I decided to study randomization of light in solar cells using a numerical toy model. Interestingly, it seems that photons do not get as randomized as I thought they would, and this leaves room for further developments in the theoretical world of light trapping in solar cells. I did it. Yes. I think I did it.
all of the students you've just seen are very passionate about their work. And why are they passionate? They're passionate because they believe that their work can make a difference. They believe that their work will one day lead to super focusing of light, cloaking with metamaterials, the widespread use of high-efficiency nanorod solar cells, fusion reactors being a power source, yielding almost unlimited energy to humans.
And everyone else.
They believe that their work could lead to a better world.
Just to end this presentation for Team TSM, I'd like to thank all of the students who participated in the making of this presentation, the directors of the TSM, and also EPSRC for their generous funding. Thank you very much.